Hi, Mr. Rob.
Hey, what up?
Hello.
Hi. Sorry to be starting late, but last hour I totally lost track of time when I was talking to calculus because instead of keeping track of the time on my computer, I was looking at the physical clock in my room, which I guess the battery on it is getting low because it's running slow. So to give all of them a chance to go not listen to me for a little bit, we're starting a little bit late today. And by the way, calculus, if I ever go over time like that, if I like go even 1 minute past the end of the period, please let me know. Because in college, the moment a class is technically over according to the schedule, you can just leave. And if they go into your like time or whatever, that professor can get in trouble if you talk to the dean. Please don't let teachers like me take more of your time than is scheduled. So today, since we're starting a little bit late, we're just going to jump right into our quick crash course on Newton's laws. And then tonight for homework, I'm going to assign a unit review from College Board. And, unlike last time where I had you guys like, stop me if I'm wrong, but last time I told you guys to turn it on College Board and then a bunch of you got to it and realized it was kind of sucky to do that because instead of uploading one document, you had to upload a bunch of different documents, right?
Yeah.
This time, I think it's easier if we all just upload our work to Classroom. So this is actually going to be a little bit like a college class. Let me tell you what the homework is first. I'm looking up the unit number so that you know which free response I want you to do. And then this time I'm going to be real specific. Just upload the work to Google Classroom, and then we'll go over this unit review on Wednesday. I also think I probably went over last period because my brain's not working right. I didn't go to bed until about 3 a.m. Because I had a cat-related emergency yesterday, which I'm only going to talk about for a quick second because it's why I'm such a dir right now. Also, it's why I think it's important to have pet insurance if you're going to own a pet, because my stupid boy cat Oogie swallowed a long piece of string, one that had knots in it and stuff. And if you don't know, that's very dangerous for an animal, including yourself, to swallow a long piece of string or rope or whatever. Because if it gets knotted up and tangled in your organs, it can block your digestive tract, which can kill you in a matter of days. So we had to take that idiot to a vet, and since all of the vets around here were closed, since it was both Sunday night during the pandemic, I had to drive an hour out of town to get him to like a center that could treat him, and then they had to do surgery, which like overall, is expensive. It's like $9,000. However, luckily I'm paranoid, so I pay for insurance wherever possible. And we have like health insurance for our pets. That's pretty good. So in the end, I think it'll be like $400. I think after I have it all said and done, I'll be able to like file the claim and get almost all of that money back. But it's really sad to think that there are people who get hit with those types of potential costs on their pet and they can't pay for it, or even suckier, they'd have to put it all on a credit card, and $8,000 on a credit card will blow up in your face real quick. But yeah, that sucked. Anyway, the homework is the Unit 3 FRQ, which is what Newton's laws are about. And please do upload to Google Drive your work. Instead of submitting it to College Board, that's easier for everybody. It's easier for me to check. And that way for y'all, it'll just be one upload with all of your work on it, and lay it out nicely. Make sure it's numbered with the subsections, and it'll make it easier for me to check. Is this okay?
Is this due tomorrow or
No,
tonight?
Wednesday.
Oh, okay.
Yeah. So, I'm sorry. No, it'll be due tomorrow night, but we're going to do it Wednesday. So find time to do it either today or tomorrow.
Okay.
Yeah, and of course, after class is over, and actually more likely closer to 1 or whatever, I'll put this on Google Drive just because we go straight from here to 4th. So I'll have to go right to teaching geometry. I probably won't get a chance to post it, but this will go on Google Classroom today. So today, we're going to continue our review crash courses. All we've done so far is talked about kinematics technically, but in our last review set that we did, we ended up talking a little bit about dynamics. We talked about forces and how they were able to help us solve that problem with the masses and the string. And in talking about the masses and the string, we talked about some different mechanical terms. Things like energy, things like momentum. But today, what we are going to talk about is Newton's laws. So we used these last week. We've been using them all year. But what I want to do is I want to kind of take a look back at our starting point and all of the things that have branched from it since in order to fit physics into a bigger context. And the reason why I think that that stuff is important is the fact that if y'all go on to be scientists or engineers, or even anything parallel to science, even if it isn't doing science in a lab, that is to say working in like working in the medical field even, you know, you will go on to do more physics than just the type of physics that we've talked about here. You will have to do physics involving electricity and magnetism. You will have to do more advanced physics involving waves. You may even be so lucky to get to talk about really complicated physics like relativity and quantum mechanics. However, those vastly more complicated subfields of physics, they follow the exact same design and logic as regular old mechanics. Now, that's a big claim, but here is the way in which all of them are identical from a mathematical standpoint. When we talk about physics, we have two things to concern ourselves with. We have the state, and we have the mechanics. This is all that physics actually is. We're taking reality and we're doing math with it to either make predictions, right, to make guesses about the future, or to make retrodictions. Retro, right, just means old. So when we make retrodictions, what we're using is we're taking some information that we have now to make statements about the past. Here is like a really big, important retrodiction. The universe is 14.8 billion years old, right? That is not a prediction. We're not using scientific information to make a guess about the future. We're using scientific information in order to determine information about the past. And that's only possible because we have a state, which in the case of the age of the universe is the cosmic microwave background radiation. If you take a telescope and point it at the night sky, in every direction there is the same color of radio light. And we take that information about that light and we apply on it a mechanics, which in this case would be Doppler shift. And the combination of those two values is what lets us reverse engineer the age of the entire universe. However, here's what Newton lays down in his 1687 hit, Philosophiae Naturalis Principia Mathematica, which is, you know, we talked about it at the start of the year. That is the first physics book ever, and that book didn't just revolutionize physics, it revolutionized all science. Here's what it said in the simplest possible way. The state of any given system are the things that you can take and turn into numbers. What are the states that we're aware of right now in physics? And there's actually enough space here to list all known state values. What are some states that we might be interested in? Things in physics that can be expressed as a number. Come on, everybody, give me some states.
Gravity.
Let's be more precise. So gravity is a force.
So like gravitational acceleration.
There we go. Acceleration would be a state. That is a number within a system that we can just turn into a value as long as we can agree on what the units are that we're describing it with. What else is a state? Something in physics that's a number.
Velocity.
Velocity. What else?
Force.
Force. What else? We have position.
Oh, yeah.
And we have mass.
Does density work?
I would say that density is a combination of two of these. So while volume is a state, mass is also a state. So that would be a ratio of two states. But yeah, anything which is a ratio or a product of two states itself is also a state. So even listing force on here is kind of redundant because we know that it's a combination of acceleration and mass now. But we're going to list it on here for a reason that I'll come back to later. What else is a state in terms of our terms? We also have energy, which is a product of states. That's 1/2 m times v. If m, mass, and v, velocity, are also states, then any product of them is also a state. We also have momentum, just m times v. That's also a state. All of these things are just numbers. Sorry, what's up?
Period, like for pendulum or spring.
So we're going to leave that one out. Time is special. Time is not a state. It's not really a thing that you can tie a number to, simply because what time is it now doesn't really make sense in a bigger picture. There is no absolute time. All that we can actually measure is elapsed time, right? So I can say some event will happen 5 minutes from now. I'm measuring the space between a time now and a time later, but we actually technically consider time to be a parameter. That is the one variable which constantly ticks forward and causes our states to quote unquote evolve over time.
Okay.
Yeah, time is weird, time is special. Time is thought of as a parameter. But oddly enough, what Newton taught us was the fact that despite the fact that we have all of these states, you only actually need one set of mechanics to describe how they interact with each other over time. That is to say that if I know the mass, velocity, and position of an object right now, I can predict what that thing is going to do for the rest of time forever, and I can re-engineer what it was doing for all of the time into the past by using a set of mechanics. In this case, these mechanics are Newton's laws. But all physics is thought of in this way. We identify states, and then we identify the way that those states evolve over time. The way that states evolve over time are called our mechanics, or I should actually write that note down. That's a good thing to have y'all take. So mechanics are just how states evolve over time. And no matter what, this is all that physics is. If you want to know what electrical systems do, you figure out what the states are. For electricity, it would be things like charge or current or magnetic field or other things that you can tie numbers to. And then if you want to know what those things do over time, you look up the mechanics. Instead of Newton's laws, we use Maxwell's equations. And as long as you take those numbers and you do those equations to them, you will get the correct answer every single time. Same for quantum mechanics. There exists a set of quantum mechanical laws. Those are our mechanics. It's called Schrodinger's equation. And if you know your quantum states, like spin or energy, you can determine what an atom will do over time. Is this okay? This is just some bigger picture stuff. But in reality, all of the fancy laws that we've come up with, conservation of energy, conservation of momentum, they are actually just a reflection of Newton's laws. So let's go ahead and list out Newton's laws real quick, just because they are so important. And you may be asked to refer to them specifically by name, so you should know the cases in which they apply. Newton's first law.
Isn't it like an object travels in a straight line?
So technically, if you took the formal statement of Newton's first law and applied math to it, you could use it to generate that information. But that is not the clearest statement of Newton's first law.
Is it that an object remains at rest and an object in motion remains in motion unless acted upon by a force?
There we go. So an object at rest tends to remain at rest, and an object in motion tends to remain in motion unless acted upon by an external force. So here's what this is saying, and the reason why we would be so explicit isn't clear now, but as you guys get better at math, you'll understand why you actually have to say all three of those phrases to make this these mechanics unambiguously correct. This is saying that if the external force is 0, if we add up all of the pushes and pulls, and that adds up to 0, then the velocity, which we have very clearly defined, the change in velocity must itself be 0. Whatever velocity you have now will continue. So if you have a ball and it's floating through space and no forces act on it, it will continue to float through space in that same direction with that same speed forever and ever and ever, unless it is acted upon by something pushing or pulling it. And if an object is at rest, it will remain at rest forever and ever and ever and ever, unless it is acted upon by some sort of push or pull. Now, this is counterintuitive because we live on Earth with air resistance and friction. And so it seems like we live in a world where mechanics says, hey, stuff eventually just comes to rest, man. It just stops just because. No. Objects only do that. The only reason why you cannot throw a ball infinitely far is the fact that the combined forces of gravity and friction are going to bring that ball to the ground, and then friction is going to bring that ball to rest. But without these external forces, the true baseline behavior of the universe is that objects continue to travel in their direction forever and ever and ever unless you do something to stop it. Item number 2, which is typically where we actually can do the math. What is Newton's second law?
F equals ma.
Not just F equals ma, but the sum of the forces is equal to ma. This is to say, if you want to know how an object is going to accelerate, you need to know what its mass is, but you also need to know what all of the forces acting on it are, not just one of them. So at all times, gravity is acting on all of the objects on Earth, but that would be to say that my calculator has a vector on it right now downwards of mg. How come it's not falling? Well, no, that's why it is falling. My calculator is falling because of gravity, but how come it's not falling out of the frame?
Your hand is stopping it.
And providing what kind of force?
Normal force.
Normal.
A normal force or a contact force. And so this thing does have a weight, mg, my blue vector, but my hand is also putting on this thing an upwards force equal to mg, oh heck, this yellow vector. And the sum of these two vectors, since they're equal and opposite, well, that sum is 0. Because it adds up to 0, the calculator does not accelerate until I remove my hand, in which case it then begins to drop again. And so this is telling us, add up all the forces. Know that the force's direction matters. That's why there's a little vector hat there. And this is going to scale the acceleration according to the mass. The bigger the mass, the smaller the acceleration. Heavy things are hard to move. The smaller the mass, the bigger the acceleration. The smaller the mass, the easier it is to move. And here's why Newton's first law is actually important to us mathematically. There could be another term here. There could be a constant, or there could be other terms that are proportional to the acceleration squared or cubed, with secret variables that we don't know about. So instead of mass, there could be secret mass 1 and secret mass 2 that affect this equation in other ways. The whole point of Newton's first law is to mathematically constrain equation 2 so that we know beyond the shadow of a doubt that when we are doing physics, well, if this is saying the change in F, when this is 0, the change in velocity, which is the same as saying the acceleration, that also has to be 0. So this constrains this equation in the following way. When we say this is 0, we're saying that this is 0, right? When this is 0, this is 0. And if this is 0 and this is 0, you would simplify this equation and what would you get?
C?
Z equals what?
I don't know.
0 is equal to 0 plus c. What does that equation simplify to?
0 equals c.
And is that a true statement or a false statement?
True statement.
It is a radically false statement. If you are solving a system of linear equations and you're like, hey, where does this line cross this line? And you start working on your system of equations and you get the following result. 7 equals 4, or 0 equals 19, What that's telling you is that there is no solution to that system. That system does not make sense. Or in the case of lines, the two lines that you're talking about are parallel, right? They never cross. There is no intersection to solve for. The statement 0 is equal to c is inherently false. So the whole point of Newton's first law, it seems redundant, it seems silly. The whole point is so that we know that this equation is complete. It guarantees that there can be nothing else to F equals ma that will work for us mechanically. This is the statement. This is the whole statement. And then finally, what's Newton's third law?
For every force, there is an equal and opposite reaction force.
Perfect. So forces exist in action, reaction pairs. And beware, the most common logical mistake that students make when applying this information for the first time, a lot of people are ask, well, how does anything move? If every force has an equal and opposite reaction force, then shouldn't the forces always add up to 0? So therefore, nothing should ever accelerate. That very much misses the point of action-reaction pairs. And here's what resolves that. I don't want to call it a contradiction because there are real contradictions where, you know, two logical statements clash. This is an invalid contradiction. You only get that contradiction if you misunderstand what the action-reaction pairs are saying. And so here is my favorite, very precise way to write it. The force of A on B is equal to negative force of B on A. And forces are vectors. So the negative indicates that one will point in one direction, the other will point in perfectly the opposite direction, a perfect 180-degree rotation of that first vector. So the reason why there is no contradiction is that the forces which are paired off as action-reaction forces, they act on different objects. So when you draw your free body diagram, you never, ever, ever have an action and a reaction force on the same object. They act on different objects. And here is my favorite example, the one that I always use because it's striking, counterintuitive, but very, very, very memorable. We live on a planet. And because of this gravitational interaction, the force due to gravity being equal to gravitational constant g, m1, m2 divided by r squared, where r is the radius separating the two. So in this case, it would be the distance from you, half of your body height, to the center of the earth. That's r. And then these masses, m1 would be your mass, m2 would be the mass of the earth, and g is a number that was cooked up a long time ago by some smart rich dudes called the universal gravitation constant, which is a really small number just designed to make the units work out nicely, right? But if you were to do this procedure, F is equal to G, M1, M2 divided by R squared, what would this equation produce for you? If you did this right now, what would you get back from this? You plug in your mass, you plug in the mass of the Earth, you divide by the radius of the Earth squared, multiply by G.
Would you get 9.81?
If you took out your mass, you would get 9.81. So if you did G times the mass of the Earth divided by the radius of the Earth squared, that would give you back precisely 9.81 meters per second squared. So what is 9.81 meters per second squared multiplied by your mass? What do we call that?
Wait.
Wait.
This would give you your body weight. Your body weight being equal to mg is an approximation when you are saying, hey, you're on Earth at the surface of the Earth, but this is the more general equation that works for everything everywhere. Now, for me personally, I'm a 75-kilogram human being, which means that I have about 750 newtons worth of body weight. If you do this calculation for me on Earth, you should get back about, not exactly, but about 750 newtons downwards of weight. Hey, what time is this class over? I'm paranoid now.
Is it 35?
11:30. 31.
Okay, I'll be 100% sure to end by 11:30 or actually a little bit earlier. And so, nonetheless, what is the reaction pair to my body weight? What is the action-reaction pair to my body weight?
Well, the force of your body weight on the Earth equals like the negative force of the Earth on your body weight.
Gravitational force.
That is the most correctest way to put it. That if you are talking about, if you realize that your body weight is the force of the Earth on you, there must be some equal amount of force of you on the Earth. Now, the reason why this is big is that a lot of first-year physics students make the cardinal sin of saying, hey, the weight and the normal force, that's an action-reaction pair. They're equal and opposite. No, weight and normal force cannot be an action-reaction pair because they're both acting on the same object. And so, the Earth may pull me down at 750 newtons, but that never, that's fine, because I am equally pulling the Earth upwards towards me at negative 750 newtons, and I'm only saying that this one is negative if this one is positive. I'm sorry, this is supposed to be approximately equal to. So, weight and normal force are not an action-reaction pair. So why do boxers wear boxing gloves?
To protect their head.
Say that again?
To protect their head.
That is literally the most correctest answer, because if you are punched in the face, right? So some amount of fist on face force is occurring. What does Newton's third law tell us?
You have the same reaction back.
The same amount of force that you apply fist on face will work backwards as well. You are going to get negative face on fist, which is how you get broken knuckles.
Mm-hmm.
And so, major misconception, boxing gloves aim to protect the face of the other boxer. If you actually wanted to protect the face of the other boxer, there are boxing helmets for that. But any force applied by one object will also be applied equally backwards on that initial object. That's why boxing gloves exist. And this third law here, because like I said, this is actually all of the mechanics, all of it. Every other thing that we have discussed is derivative of the Newton's laws, which is to say that the two big conservation laws that we got, and that we use everywhere because, conservation laws are nice. They're easier to use than the pure mechanics, but they give us the exact same results. And in some cases, they are a much more elegant way to solve for the final answer. The reason why our conservation laws will always give us back the same answer as kinematics is the fact that they are themselves exactly the same. Let me show you what I mean. And we're going to do this starting from Newton's third law. And we're also going to use a little bit of Newton's second law. But those conservation laws, they are these laws dressed up with a little bit of algebra and makeup. And which one would you all like to talk about first, momentum or energy?
Energy.
Energies. I'm going to start with Newton's third law. For any amount of force, the force of A on B, this must be equal to the negative force of B on A. So that is to say, if an engine applies force on a wheel, that wheel must apply the same force backwards on the engine. When you walk, you are pressing against the ground in order to take advantage of friction. And by pushing against the ground with your foot, the ground pushes against you, which is what drives you forward, which is a really weird thought. But I'm now going to take, and I'm going to multiply both sides of this equation by distance. I'm going to take both sides here and multiply by delta x. Is this okay? Okay. Now, the reason why this is cool is that force multiplied by distance is actually what? It has a name, force times distance. Force multiplied by distance is equal to work. So if you apply a force on an object, force multiplied by the distance parallel to which that force is applied over is going to give you work. So this step of algebra here, this is going to give us the work. This is going to give us the work. And luckily, if one object is applying a force on another, and we imply that they have to be in physical contact to do this, then the distance traveled by each will be the same, which is why I'm not going to give two different delta x's here. The change in position of both objects, assuming they're in contact, must itself be equal. So on the left-hand side, I'm just going to leave that as work. That's great. So I have force times delta x. But on the right-hand side, I'm now going to take advantage of Newton's second. What is Newton's second?
All the net forces are equal ma.
So this is going to be equal to negative ma delta x. And now let's take a deep dive and look at this a delta x. In order to get this, a good swap out for this, let's go ahead and look at our time-independent equation of motion. V squared is equal to V sub O squared plus 2 a delta x. Yeah? Do you see an a delta x in there?
Yes.
Let's go ahead and solve for the a delta x, and then we'll make a swap here. So v squared minus v sub O squared will be equal to 2a delta x. And then to get a delta x alone, I'll have to divide both sides by 2. Hit it with a 1/2, hit it with a 1/2. And would you look at that, a delta x is equal to v squared minus v sub O squared divided by 2. That factor of 2 just comes from kinematics. And now I'll substitute. So force multiplied by a change in position is going to be equal to negative m times v squared minus v sub O squared all over 2. And if we get really fancy, we can say F delta x, work is going to be equal to 1/2 m v sub O squared minus 1/2 m v squared. What is 1/2 mv squared?
Energy.
This is energy.
Kinetic energy.
That is kinetic energy. So please notice this right here, this is the work energy theorem, which is the same statement as pure conservation of energy, but in reality, this comes from the mechanics of Newton's laws. It's just Newton's laws plus kinematics, which are pure math. Is this okay? Okay. Item number 2. Newton's third law is also conservation of momentum in a disguise. So F of A on B is equal to negative F of B on A. And multiplying by position gives us work. What's the momentum equivalent?
Mass times velocity.
Mass times velocity is momentum, but what changes the total amount of momentum? The vocab word I'm fishing for begins with an I.
Is it inertia?
Inertia is what mass measures. So a heavy object has a lot of inertia, not the I word I'm looking for.
Impulse.
Impulse. I'm going to multiply both sides by delta t. By delta t. This is to say, how much time is the force applied for? And if you think about it, time and position in this case should be related, right? Because if you apply a force for a long time, you'll apply it over a large distance. And if you apply a force over a large distance, you'll apply it for a long amount of time. However, the two are not perfectly one-to-one. which is why these two different formulations will give us back different equations. But on the left-hand side, this is just impulse, pure impulse. Pure impulse. But on the right-hand side, I'm going to do the same thing that I did before. I'm going to take advantage of Newton's second law and say that F is actually equal to ma. So on the left-hand side, we get F delta t is equal to negative ma delta t. And this time, let's go ahead and look at Kinematic Equation One, the one that does not involve position. V is equal to what?
Sure.
I think it's the first line of the AP equation sheet.
Initial velocity plus acceleration times time.
Okay, so what I want to do here is I want to solve this for acceleration times time. Oh, look, acceleration times time. So that's just v minus v naught. And now I can plug this into Newton's third law, and I can invent new equations of motion. F delta t is equal to negative m times v minus v naught. And so I can distribute through that negative m, and F delta t is equal to mv naught minus mv. This right here is the impulse momentum theorem. And this is also conservation of momentum, because when you do a conservation of momentum, what you're saying is if there's no force, this is zero. And so the momentum gained by one object must be equal to the momentum lost by another object. And we could show that because if this was zero, this would show us that mv is equal to mv. So in reality, everything we have done since Newton's laws is actually just a reuse, a repurposing, a rebranding of the exact same mechanic. F equals ma. If one object does a force on another force, if one object does a force on another object, we get that same force back on that first object and in the opposite direction. And if the force is zero, there is no acceleration, period, point blank. Those are literally the mechanics that make the universe go round. Nothing more, nothing less. And so the main skill to take away from here is choosing to use these different representations when it's convenient. But you should also know that using one over the other, where both of them work, will always give us the same answer as long as you make no mistakes. But what can be annoying is getting this F, or the sum of F, which is why we draw free body diagrams. And this is where we will pick up tomorrow. When it comes to free body diagrams, all we're doing is we are labeling the center of mass of an object on the origin of a coordinate axis that is to say that we put our center of mass at 0, 0, and then we affix all force vectors starting from that center of mass. You label on there all the force vectors, and everything about those vectors is mathematical. A force has a length and it has a direction that you have to get correct when you label it on there. The length is important because a bigger force must be represented logically by a longer vector. Sum the forces trigonometrically and this alone is what gives us the sum of the forces. The whole point of this being so that we could then use Newton's second law to get F equals ma, because once you have that A, once you know the acceleration, that is enough information to figure out what that system is going to do for the rest of time, forever and ever. The other thing that's important to keep in mind here is that when you affix the force vectors, you only put on the vectors and not components. If you do that, you are double labeling forces. So the big place where this comes into play is with ramps. When we talk about a block on a ramp, we take the weight and we split it up using what functions? I have a vector pointing this way, but I need to know about it these other two directions. So what do?
Use geometry.
Specifically, what subfield of geometry?
So sine.
Sine and
Cosine.
cosine. Sine and cosine are the two things that allow us to break up vectors into their components. If you are ever drawing a diagram with mg or mg sine theta, mg cosine theta, for whatever reason, it is one or the other, not both. Never both. Never both. Never both. Never both. If you are drawing a free body diagram and you put mg on here, and you put mg sine theta and mg cosine theta on there, you're basically double labeling the weight. You're saying that object is twice as heavy as it actually is. You either put the force or you put the components, never both. Never both. Okay? In the warm-up question, I'm sorry, in the homework, which is Unit 3 free response question, that has free body diagrams in it, and take a wild guess what tomorrow's warm-up is going to be.
Free body diagram.
Free body diagram city. We're going to do some free body diagrams where we do a couple of just like physics questions, but I also want to do a couple of like real life situations. Like, what is a free body diagram for your car? Because I guarantee it's pretty complicated. Anyway, you all have a nice day. Look for that homework to go up. And tomorrow I will do my best to get the scheduling all correct. It should be easier for me to focus on what's important once I get my cat home. And I might be able to pick him up today, and that would make me feel a lot better. Anyway, you all have a very nice Monday, and I'll see you tomorrow.
Thank you.
Thank you.
Sure.
Yep, bye.